Welcome. We're going to be looking at H-bridge motor control using a ULN2003A transistor array versus MOSFET input. I'm doing this hardware review to sort of piece together several web pages and earlier YouTube videos that I've done. This is going to refer to the ULN2003A. This is its web page address. It's also referring back to why your MOSFET transistors get hot. The links will be in the description. This review is here so when we start programming microchip PICs to operate this hardware, this will illustrate why I take the steps that I do. And so this was a question or a comment a comment from a visitor, and it goes as follows. This is the reason why in an H-bridge configuration all MOSFETs are usually in-channel MOSFETs combined with a dedicated MOSFET driver and an internal bootstrap circuit. These bridges can work with much better efficiency. Also, it's necessary to add some dead time of several nanoseconds between MOSFET gates to avoid the shoot-through effect. I'll explain in the following circuitry how I addressed these issues. First, I'd like to thank the visitor that left this comment, and I would ask you to please hit the like button, subscribe, and share this video. Alright, let's get moving. This you saw if you watched the last two videos. Here is my microchip PIC, 3 optocouplers, 2 for the H-bridge, 1 for the constant current power switch. In this case, I'm going to simplify it for some people. I'm going to eliminate the optocouplers and eliminate this, and we'll use a little different approach, but the programming is identical. The basic H-bridge is what you see here. 2 N-channel transistors, 2 P-channel transistors. The two that I'm using are the IRF4905. That is a P-channel MOSFET. It has a resistance drain source on of 0.02 ohms. The other is the IRFZ44N. That's the 2 N channels down here. And they have an RDS on of 0.32 ohms. I've had this circuit out for years. When I initially put it out years ago, I noticed a problem that the P-channel MOSFETs were getting hot, and these were getting warm. And after some feedback from visitors and so forth, I researched the problem, and this is the problem that I found. The original transistors that I used was the IRF630. That's for the N channel. It has an RDS on of 0.4 ohms. And the P channel was the IRF9630, the IRF9630 with an RDS on of 0.8 ohms. That's a big difference between 0.02 and 0.032 ohms. I switched out these transistors, and that fixed that problem right off the bat. And so that answers the question of efficiency. That alone is going to increase your efficiency, and that's what was explained to a greater degree in the video, why your MOSFET transistors get hot. Alright, note looking at this as it is. Both of switches are open. SW1's open, SW2 is open. Q3 and Q4 are turned on all the time. That's what does your braking action when you turn the H-bridge off. That creates the braking action for the motor. I believe these two up here being on with these off will accomplish the same thing. But a switch is a switch. I don't want to play with push button switches, so let's go with some transistor or electronic switches. Here's an expanded view of that same H-bridge. I won't go over these parts again. In this case, I'm utilizing a couple of different things. Now I have a power switch in the high side. I'm using another P-channel MOSFET, the IRF4905, as a high-end switch. But I'm using, for my switching to the H-bridge, a ULN2003A. Alright, what that means, if I have an input from the microcontroller of high, and you don't need input resistors or anything, the output will go low. It'll switch to ground, high in, switches to ground, turns the power MOSFET on in the high side, supplies power to the H-bridge. High in on DN1, low over here. This will switch this point to 0. It turns on Q1. Q4 is still open, creates a path from Q1, motor, through Q4 to ground. Do the other switch with this one open, of course. This transistor will turn off. Q2 will turn on. Q3 is still on from before, creates a path through Q2, the motor, to Q3 to ground. So the ULN2003 provides a fair amount of isolation between the microcontroller, and it can switch a lot higher voltage. Here's the spec sheet to the ULN2003A. It is a 16-pin device. Each output is rated at 500 milliamps at 50 volts. Way more than what we need here, of course. Like I said, I have a whole web page on that in the description. Here is the internal equivalent logic in the ULN2003A. You notice these clamping diodes up here that go to common. Leave that disconnected. You're not driving magnetic loads here, and it shouldn't create a problem. And of course, the input goes straight to the microcontroller, no dropping resistors or anything needed. And the output, when this is high, will switch to ground. It inverts. Looking over here, here's the equivalent circuit for each transistor array. As you see here, there's an input resistor, 2 transistors in a Darlington configuration, and various bias resistors, and it has suppressor diodes. What is my alternative? There is another way I don't need, but let's look at some prices first before we go anywhere. A ULN2003A is 56 cents from DigiKey. That's cheap. Note the IRF4905, that's the P channels, are $2 each from DigiKey, but you can get them for 50 cents a piece off of Amazon, eBay. Mine were bought off of eBay. I had no problems with them. I got them for about 50 cents a piece. The IRFZ44N is 77 cents each in quantity 10 from DigiKey. Those that I have also came off of eBay, and I think I gave 50 cents a piece for them. All right, in this variation, I have replaced the ULN2003 with 3 separate in-channel small MOSFETs. In the case here, for instance, a high in will produce a low out on the drain. It will switch on U4 and supply power to the H-bridge. In this case down here, a high in here, it will do the same thing as pressing SW2. A high here, low there. This transistor turns off. This transistor turns on. This one is still on, assuming that's low, and creates a path from Q2 motor to Q3 to ground. Same thing over here, a high input, low over here. Creates a low there, turns off Q3, turns on Q1, Q4 should still be on, Q1, motor, Q4, ground. Alright, the question is, why would I really want to switch the power on and off? There's a reason why. If you remember the motor demo, it had a braking action in it. So the first thing I do when I change direction is I output a low on DIN 1 and a low on DIN 2. This turns both of these back on. These create, those two transistors being on, creates the braking action to stop the motor rotation. And so I put a delay in it, and then to let the motor stop. Then I put a low out here and switch the motor power off. While the motor power is off, I change direction whichever way I want to go. So if I want to reverse direction, I'll simply put a high out either on DIN 1 or DIN 2. Then I will reapply the power, and off the motor goes. I've never had a problem with shoot-through. Shoot-through is where, say, Q1 and Q3 are both partially on when we're switching them, and that creates a dead short to ground, possibly blowing the parts or blowing traces off the board or whatever. So this, using the combination of the high-end switch and proper programming, assures that there will be no shoot-through, that the braking action will give it time to stop, because if you immediately reverse direction, with say you want to go counterclockwise and this thing is still spinning clockwise, I mean, you're going to throw a lot of current and spikes through the system. You don't want to do that. So the sequence, again, for programming is you will turn off both inputs. This will enable the braking action of the motor. The motor will stop. You disable power, then you switch direction whichever way you want to go, and then re-enable power in those steps. Finally, here's what the little transistor looks like. It's a TO92. It has an internal diode as well. It's rated at 60 volts, 200 milliamps, and they are 61 cents each from DigiKey. Now, I bought a bunch of mine. I think they were 10. I bought 20 of them for $2 from eBay. Mine work fine. But I'm not using them in an industrial configuration or something. It's just hobby stuff. So, but this is not bad. But a single N-channel little MOSFET like this costs more than the ULN2003 at 58 cents. So it'd probably make more sense to use the ULN2003. To finish this off, there's another thing you have to understand. There is no electrical isolation between the microcontroller because they have to share a common ground. They're not, when you're using optocouplers, you can isolate electrically the H-bridge and the power switch from the microcontroller. But in this configuration, this probably works fine. If you're in a really environment where you're throwing a lot of noise around, you might want that optocoupler isolation. All right, appreciate you listening to this. I hope you got some use out of it. Visit my website at www.bristolwatch.com. That's my alternate site. And you'll have these links in the description to get further information. Have a great day.